Welcome, everybody. Come on in, take a seat, join the ride. Let's see where we can take this. So I do have some slides, but it will be mostly live, so let's see how much stuff we can break today. I'm Philip, I work for Elastic, and I kind of want to give you an impression about the Elasticsearch, evolution, revolution, wherever we can take this. So let's start off with the revolution. Which I think is kind of the fitting picture. At first, there's always the revolution of how systems get started. So who knows this site? dbengines.com, anybody? It's like the Tiobe index for data stores. So the Tiobe index is for programming languages. This one is for data stores. And you can see how popular databases are. And you can see there is a mix of relational ones, non-relational ones. Luckily, Elasticsearch is now in the top 10. You can see we are currently at 9. We were at 8 the previous month, but it's always a little of an up and down. So this is kind of how we got, or to see how we got this far. By the way, the only system I think that should not be in there is Access. Just in general, and also because sometimes you see stuff like this, like query is too complex. This seems to be a feature of Access, and what you get when you use such a data store. Okay, so generally, who uses Elasticsearch? Quick show of hands. Well, that's a good number. Let's see. By the way, who is using still version 2 or earlier? Just to get an impression. Okay. Who is on 5? Who is on 6? Who is on the very latest version? Okay. Good. Kind of a broad mix, so we'll have something for everybody, I guess. So I'm working for Elastic. I'm part of our infrastructure team, and I always say this is a Unix pipe. I kind of piped it out into developer advocacy, but now it's conference season, so I'm pretty much spending all my time at conferences just to speak about the good stuff that we do. So does anybody know how we got started with Elasticsearch, or we is good? Shai, our CEO now, how he got started with that? So the story is like, it's kind of like the modern fairy tale. His wife wanted to become a chef and went to London to work in a restaurant to become a proper chef there and do training. And like any good husband, he said he wanted to help his wife, and the problem was she had a lot of recipes, and then she had some ingredients, and she had a hard time finding in her recipes what she could cook with them. And so he built some system to search her recipes. It was slightly over-engineered. And she never got that recipe search, actually. She's still waiting for that, and it has been a couple of years. But this is how it all got started. Basically, started with the recipe search and kind of got into search based on that. And, well, Elasticsearch is kind of the child of that. Actually, it's the third implementation. So there was Compass 1, Compass 2, and Compass 3, since 3 is kind of the magic number, was then called Elasticsearch. So it's kind of the third implementation about all the stuff that has been improved over time. So this is the logo. If you know our current logos, you can see that our Photoshop skills have also improved a bit. But this was the initial logo, and if you see some older slides, you will probably still see that as the Elasticsearch logo. But we've changed a bit over time. So in case anybody is not familiar, since not everybody raised their hand when I asked if they're using Elasticsearch, so generally we have a cluster. These are all the instances working together to answer your queries. Then a cluster is made up of nodes. Generally, a cluster consists of one or more nodes, virtual machines, containers, whatever, to answer queries. But for us, it's one Elasticsearch node that is answering that, or forming that cluster. Then you have an index. Basically, this is like a collection of data that belongs together. You have a shard. Every index can be split into one or more shards. You have a document, which is a JSON document, since nowadays everything needs to be JSON. And every document then has an ID. And these are basically all the terms we will need for this talk to see what is going on. So if you run just, excuse me, the general get against the node, you can see this is what you get back, and you can see this is our tagline. You know for search. And it has always been for search. So if you're searching on the internet, there's a good chance, unless you're using Google, that search is somewhere, or Elasticsearch is doing the search for you somewhere. So if you're searching on any of these sites, behind the search box, there is Elasticsearch doing the work for you. And over time, we figured out, well, there are other things that people want to do. So we have Kibana for the visualization and Logstash to kind of get a lot of data. And that formed then the infamous ELK. So I guess that one makes it pretty clear. This is the ELK, and commonly referred to as the ELK stack. And then these companies started using the Elk stack. So Mozilla, they have some security projects around that, Slack also for events, and Blizzard, if you're playing their games, like all the operational stuff to monitor are your games working well, they also put everything into that Elk stack. And then this little fellow came along. That's Beats, since not everybody is using Java, I know here. Most of you are probably using Java, but not everybody wanted to put Java on their servers just to collect log files. And sometimes it might have been a bit more powerful than they needed. And Beats is kind of like the slimmed down agent to just forward data and not do any of the hard parsing. And that's where this Beats agent comes into play, which is written in Go. So you get native binaries. The problem then was the Elk doesn't contain a B. And then we came up with this one, the Elk B or Belk. And we even had a custom logo for that. So that's the Belk or the Elk B. You probably have never received a sticker because we didn't have official stickers of that. But some of my engineering colleagues actually made those as a sticker on their own. The problem is then Elk was kind of cute and everybody knew that. And Belk or Elk B could have worked. The problem is we're always about scaling, and this is not very scalable from a marketing perspective. Because what happens if you add another open source tool then to the mix? You would add another letter, you would need to create another animal. It's getting harder and harder to get those animals. And you know, getting rid of an old name can take a long time. Like, you know, all the recruiters who are still asking, can you do J2EE for me? It has been 10 years and people are still referring to it with the old name, and probably with all the animals that we make up, it would take forever until we get rid of the old names. So now we call the entire thing the Elastic Stack. So that was kind of the revolution, and now it's time for the evolution part. Let's see where we can take the evolution. By the way, if you have any questions while I do the demos, and I have a lot of stuff, so I will mostly just walk through my demos. If you have anything during the demos, if you go to sly.do/my Twitter handle, you can just input any question there, and I will see that afterwards. And if I have time at the end, I will answer it here. If I don't, I will just tweet out whatever you have asked with the answer. So this one you can take a picture of, because that is where you can put any questions during the talk, and I will answer probably on Twitter afterwards. So this is generally where we get to do the questions. If we have time, we'll also do questions at the end. But this is, in the meantime, where you can do questions. Cool. So the evolution part is a bit about kind of growing up and maturing. And we have learned a lot along the way as we have grown up and matured. So let's see what this is. So the first thing is strictness. Initially, when we started, we were rather more on the lenient side because, well, we wanted to be easy to get started, and we would accept a lot of stuff that kind of worked, and we would just try to work around any user errors and just make it easy to get started. But at some point, strictness is really what you want. So for example, to avoid bad stuff, you want to check what is going on. So the first thing is we are now checking configurations and parameters. And I will just run all of these queries live from Kibana. So you can see I'm running the latest version in 5.6. I have 3 nodes running here. Let's add the headers. Oops, that's not what I want. Or that is what I want, even though it's hard to read. So you can see we have 3 nodes in total here. Elasticsearch 1, 2, 3. I have just 3 Docker containers basically which I have running, and we'll run all our queries against those. By the way, if you want to see what that looks like, I'm using our official Docker containers which come from our own registry, which is based here. We will update the version during this talk, and otherwise I'm just having like 3 nodes which I'm using. Heap of half a gig. Every one of these Docker containers has a gig of memory, so 50% heap, 50% file system level caching. I've set some configurations, but most of the stuff is pretty much what you would expect. And I have just 3 nodes here, and at the very end I have 1 Kibana instance. This is what I'm querying, so that should be pretty simple. Okay. Right now, our server is in a good state, like everything is green and working as is expected. So coming to strictness, can you spot the typo in this query? Yes, it should be tokenizer, but this is a pretty simple example, and it will just like, since 5.0, we will tell you if we do not recognize a parameter. In previous versions, if we didn't recognize a parameter, we would silently throw it away. And you would be wondering why this is not working. Because if I run this now, it will actually tell me, okay, I don't know this token sire whatever, but thanks to the Levenstein distance, it can actually tell you like something is very similar to that. You've probably seen that on the, if you are using the shell and type in a git command and you mistype, it's also suggesting like something very similar is around there. And we're doing the same now for parameters here, but we also do the same for configuration files or any configuration that we have. Because also for us, it was kind of a pain in the butt if you have a 200-line configuration file and you had a typo somewhere and the parameter was silently ignored, it was very hard to figure out what was actually going on there. So if I correct that and call it tokenizer, it's deprecated, but this is working as expected. And we're just generally doing this strictness. And if you're using Elasticsearch, you have probably also ran into this other thing, the Bootstrap checks. Anybody had issues with Bootstrap checks before? Okay, nobody? Okay, good. Because Bootstrap checks are here to stay. Bootstrap checks are basically you start the node up and it will check, is your system configured in the right way? And if not, we will not start up the node if you're in production mode. So production mode is assumed when you can form a cluster over the network. Then we assume you're in production mode. And if we know, for example, you don't have enough file handles, or you run with a JVM version where we know this might corrupt your data, or we have a lot of checks that we know stuff that will cause you a lot of pain later on, we will simply not boot up the node and instead say like, okay, you need to fix this now to avoid a lot of pain afterwards. The other thing we added in 6 are rolling upgrades. And we can actually demo that live. So rolling upgrades pretty much look like this. You keep on running, and everything keeps working, and you will just keep rolling and upgrade as you go along. Sometimes you look up, and hopefully everything works. Let's see how that works. So let's do that. I need some data, which I will quickly insert here. We'll come back to that in a little bit. So the first thing, before you do any upgrade, we have the upgrade assistant here. And you should run that because the upgrade assistant can actually tell you what you need to change in order to upgrade something. You have this cluster check up here, and it tells me basically there is one error here. You need something about the Kibana index, which basically stores the configuration for Kibana. And now it links to the documentation to tell you which commands to run. But actually, it has a reindex helper which can do all of that for you. For example, I can just say reindex here, and it will fix everything in the background for me. You can see it's running, and it has replaced that. If I go to the cluster check back again, and I can rerun that, you can see, okay, we have nodes, but no errors or warnings anymore. So now we can actually upgrade our system. So the first thing I want to do is I want to replace my Docker containers and see what is going on here. So let's quickly see. We have my 3 nodes here. You can see the third node is my master node. So when I replace and restart that, something else one of the other 2 will be elected the master node. Let's hope it doesn't take too long. So to do that upgrade, what we need to do is I have this .env file where I basically say I want to switch from 5.6 to the very latest version, 6.2.4. And then I can simply replace that Docker container. And basically, it's killing the old node and is replacing that with a new one. And here in that view, you can actually see that, yeah, lots of stuff is happening. We have killed the Elasticsearch 3 node somewhere. If we scroll up a bit, we might see it. You can see here Elasticsearch 3 exited with code 143. We basically hard killed the node. And even while this is going on, you can still check how many nodes do I have in my cluster. 2 at the moment. And you can still read and write data from your cluster, even though 1 node is being replaced. And once the Java process has come up again, it will join the cluster again, and you can see now I have a mixed version numbers in my cluster. So the 1 and 2 nodes are still on 5.6, but the 6.2 node, that one is already on 6.2. And this is the first major version where we can do that. Before, you always had, for a major version upgrade, you had to stop everything, upgrade your nodes, and then restart them in a new version. That's not required anymore. Okay, so while we're at it, let's replace the next node. And well, it's a Java process, so it takes like 20 seconds or something like that until it comes up again. But once again, we can just query the nodes and see, okay, now we have 1 on 6 and 1 on 5. And in the background, this is already restarting our node. So you can see Elasticsearch 2 is loading the plugins and hopefully is coming up soon again. Okay, it found something that is deprecated, but in 1 or 2 moments, it should then say that it has correctly come up again and then join my cluster again. Okay, so yellow to green, that looks probably good. Let's see. And we have that node again. So when we replace the first node, I need one trick. Since Kibana is talking to my Elasticsearch 1 node, Kibana will also disappear while I upgrade that node. So let's quickly replace my first node. That should be pretty quick. And now Kibana will not work anymore because Kibana is trying to talk to this one specific Elasticsearch node. It unfortunately cannot load balance between any other nodes right now. So Kibana is no use right now, but we can fall back to the shell and just see what we have. So you can see 2 and 3 are still up and they're on a new version. And we'll just keep running that basically until my Elasticsearch 1 node is coming up again. And you can see Elasticsearch 1 is, here it says it started. Then Kibana found that one again. And one thing Kibana tells me now is that Kibana is like running in the wrong version or in another version than Elasticsearch. So we'll need to upgrade Kibana as well. So let's see first, did we reach Kibana again? Yes. Kibana 5 can still talk to the Elasticsearch 6 cluster. That's working fine. It can also read the data and, well, see what is going on with that. But we also want to upgrade that. So the final step is I'll just replace that node. And if somebody complains to you that Java takes a long time to start up, you will see how long it will take for that node application, which is Kibana, to actually get back up. Because that is taking much, much longer and will be sitting around for quite some time until that one gets back up. So let's scroll to the end. Okay, we have exited Kibana. And now this node application will kind of crawl back up. And this will take a few moments. But after that, we have upgraded all the data. You might have seen in previous versions, like, why are upgrades generally problematic? Lucene can always write its current version and read the previous version, but it cannot read 2 versions back. And since every major Elasticsearch version packages a new major Lucene version, we can always read the data from the previous cluster version, but we can write to that with the new version, but we cannot read data from 2 versions back. That would need a bit more work. Then you would need to reindex your data, for example. So let's see if Kibana is coming back up again. But no, like I told you, node can take a bit of a time. Well, let's see. Okay, stuff is happening. Yes. By the way, you can see the color scheme changed again. I always say version 3 was black, 4 was white, 5 was colorful, and 6 is blue. Why blue? Because if you have some problem with colors, like the colorful was very hard to see if you were colorblind. This one should be much better for colorblind people. Okay, still keeps my history. So we have successfully upgraded my cluster live, and that worked. So this was probably the most dangerous part of this presentation. So next up, flood stage watermarks. Who has seen watermarks in the past already? Anybody recognizes watermarks? So what watermarks are basically doing is everything is flooded and you don't want to fail over in a bad way. That is pretty much the idea of what you want to do with watermarks. So we had the upper 2 flood stage watermarks, or watermarks we had before. So if you reached 85% of the disk space on a node, we would not allocate new shards on that node. If you have the high watermark, we would actively try to migrate shards away to a node with less disk usage. And now in 6, we have added this flood stage. Basically, when you hit 95% disk space usage, we will actively block write operations, so you will not be able to corrupt your data. And you can actually demo that as well. So let's quickly demo that. No, that's not what I wanted. So let's say we have an index, my flood. We insert that. And then we can actually check how much disk space do I have on my poor little laptop, which is not all that much. But if you scroll down here, you can see this is the Elasticsearch 0 node, basically. And you can see in total, I have 31 gigs of disk here, and 19 of that are free. So what I will do is I will not use percentages, but I will use like a hard gigabyte amount. And I will now set the low watermark to 100 gigs, the high watermark to 50 gigs, and the flood stage watermark to 30 gigs. So I will immediately hit the flood stage watermark here. So I will apply that setting, and it's changing that. And as you can see, this will update every 10 seconds. So it will maybe take a little while until this gets applied, but you can keep reading data, but when you try to insert data, this will, as soon as this setting is being applied, will fail. So let's try that, and you can see now my write operation is actually forbidden, because rather than destroying my data or potentially corrupting my data, I will just block write operations. You can still read, but you cannot add or change any data anymore. Okay, let's try to revert it again, because maybe I still want to write to my cluster for the demo. Basically, I think in 5, we added that option to reset any value. You can just set it to null, and that will unset the value to the defaults. So I have applied that. If I try to write this document now, will this work or not? Who thinks this will work? Who thinks this will fail? Yeah, let's see. It's still failing, because the problem is once we have locked an index, it will stay locked, and you will need to manually unlock it. This is kind of a safeguard. So if you have a shard of an index on any node that has hit the flood stage watermark, that index will be locked if you do a write operation to it. And here, basically, you need to say read-only allowed. Read-only, allow, delete. These are the only operations I was allowing. I need to reset that. Once I have reset that, then you can actually write data to that again. And now you can happily write data to your cluster again. So this is the flood stage. This is just one more safeguard that we have added to Elasticsearch. Okay, sequence numbers. Anybody heard of sequence numbers? So sequence numbers are, sometimes it's hard to keep track of what is going on in your cluster. And we have made this very nice GIF to show you how sequence numbers actually work internally. It's mostly for correctness, especially around failovers. So what you have is you have the primary node or the primary shard on the left, and it replicates, or it has 2 replicas, and it replicates its data to these 2 replicas. And you have a local checkpoint and a global checkpoint. And basically, the local checkpoint is applied after each write operation, and on the next operation is kind of like the global one is piggybacked with the other requests back, and you can see, okay, it's writing out data. The global checkpoint means it has been written anywhere. And once they have kind of like advanced their local checkpoints, then that can be told back to the primary shard that those have been applied. Now we have a failure. So we managed to write the data or some data to each one of these replicas, and now my primary shard fails. The middle one now becomes the primary shard. This has never seen the write operation for. And since this is the primary shard now, this will actually throw away the 4th write operation on the other replica to keep them in sync. So basically, in the end, what you have a new primary, you have another replica, and their data is now in sync. It was very hard to keep that in sync previously, because we didn't have this counting to know which operations had been applied and have they all been applied in the right order. So this is the general approach of how sequence numbers work. And you can actually demo sequence numbers quite nicely. So let's say we have an index called sequence numbers with 1 shard and 1 replica, and I'm excluding my Elasticsearch 1 node. Anybody has an idea why I might want to do that? Because Kibana is connected to that, and I will be killing nodes again, and otherwise I won't be able to see anything in Kibana again. So what I'm basically saying is only allocate this index to the Elasticsearch 2 and 3 nodes. Otherwise, Kibana will go blind again, and we want to avoid that. So basically what you have here, if you look at that, you can see here we have 1 primary shard, 1 replica shard. Our primary shard is Elasticsearch 2. We need to remember that because I want to fail that over pretty soon. And now you can start writing values. And the result of that write operation looks pretty much to what you have been used to before. The only thing that has been added are these lines 12 and 13, where you can see sequence number and primary term. Sequence number is something that is counted up with every operation. This is, by the way, on a per shard level. Since we only have a single shard, this is always the same now. So every write operation I do counts up. The primary term changes every time my primary shard changes between nodes. So what happens if I write to one specific ID? Every write operation counts. If I delete that document, is it the write operation? Yes or no? Will my sequence number increase? Yes. I've deleted my data. What if I do the delete again? Will the sequence number increase again? Or will it stay the same because, well, there is nothing to do anymore? Yeah, every operation counts. So even though it's not doing anything, the sequence number still keeps increasing. OK, so Elasticsearch 2 was the primary shard here, so we will stop that one. And once you have stopped that one, you can actually check out like how do my shards look like. Why is the replica now unassigned? What is the reasoning behind the unassignment of the replica? Yes, so I have stopped the one, or basically my rule set is that data cannot be allocated to Elasticsearch 1. It can only go to the nodes 2 and 3. I have stopped 2, so it can only go to 3. This is also where the primary shard is. And we're never allocating a replica on the same node, because that doesn't make much sense. If that node goes down, the data will be unavailable for that one as well. Now I can keep inserting data into my Elasticsearch 3 instance. And we keep inserting some data. And now it's time to restart my node. Once again, this will probably take some time since, well, my Java process needs to get up again. You can see the connection closed. Now Elasticsearch 2 is starting up again. And we can, well, let's quickly check when it will come up again. So yeah, at some point, the node will be available again. So it's starting, it's publishing its address. It should tell us at some point that it joined the cluster again. Yes, and now the Elasticsearch 3 node actually found that node again. So now you can see Elasticsearch 2, the 2 node is, here's the Elasticsearch 2 node, that is the replica now. That is what we wanted. And now there is one very nice attribute of this entire thing, both not only for correctness, but also for the speed of recovery. So with this command here, I can actually check where the operations came from, because before, when an operation or when a node was not down and didn't get write operations, what it was doing basically is, as soon as it came up again, it went to the other node and said like, hey, I have missed out some write operations, give me your data. And what we were doing is, we were actually comparing the segments, the Lucene segments on disk, and since they were written independently, they were often not the same. And we would just hash those Lucene segments and compare the hashes. And then we often had to transfer a lot of data between nodes, which actually was kind of the same. Just because one node missed out on 3 write operations, for example, we would need to transfer a lot of data, like megabytes or even gigabytes. What we now have, since we have this transaction log where we have the sequence numbers, we just keep all these transactions and we can just replay the missed out transactions. And what you can basically see here, this option, the translog ops recovered, basically says there were 14 write operations while Elasticsearch 2 was down, and those 14 write operations have been applied from the transaction log. We didn't need to do any file-based comparisons. This was just replayed from the transaction log. Which is cool. The only thing you need to keep in mind is that there is a trade-off for that. Disk space, because this again is per shard. So by default, every single shard you have will keep up to ½ a gig of data in the transaction log, or up to 12 hours. Whatever hits first, you will throw away the data. But you can do the calculation. If you have 40 shards on one node, that means 40 times ½ a gigabyte. So you will need 20 gigs of additional space just for the transaction log. You can, of course, change those values, but those are the default values, so you might need more disk space than you used to have before. And then the other thing people sometimes ask is, what happens if I run out of transaction numbers? What if I reach the maximum? Because this used to be especially a thing in Postgres, which has this XID, the transaction ID, which I think is capped to 2 billion. And if you don't run an auto vacuum, you will hit that limit, and then you will not get to do any write operations anymore. Do we have any mechanism to work around this limit? No, we actually don't, because we're using a long. So you have 2 to the power of 63. And that is per shard. And I think if you do 1 million write operations on a single shard per second, that would still give you like 200,000 years or something like that. So this is not a practical problem. We don't have a fallback mechanism if you run out of these transaction IDs or the sequence numbers. But you should not really hit that. And another feature that we're currently building is cross-data center replication, because once you have this transaction log, you might be able to replicate the data from one data center into another one. We still don't recommend to span one cluster across data centers, because if you have latency, which is like 2-digit milliseconds, or your link is not very stable, very bad stuff will happen to your cluster. So generally, one cluster should only span one region, which can include multiple availability zones on AWS, because that's still more or less one region, but it shouldn't be across regions. But that cross-data center replication will then allow you to asynchronously replicate data to a different cluster in a different region for a disaster recovery scenario. We're currently building that. We're currently implementing some Lucene primitives we want to use for that, but we'll see if we get to that in 6.x or 7.x, but cross-data center replication will become a thing at some point. The other thing is that types will go away, or multiple types per index, actually. Who is using multiple types per index? And if you do, the question is why? Because we have been recommending not to do that for a long time, and now we're finally getting rid of them. So it's basically because we kind of lied, because the multiple types per index are kind of a lie. Lucene doesn't know that concept, and people who know Lucene were always very confused by that. And our initial approach was because we said it's a bit like a relational database, and that comparison was very bad, but you will still find that out there, because we pretty much said like, oh, the database is pretty much like the index, and the type is pretty much like the table in the relational world. This was a very bad comparison, but it made the mental model a bit easier initially, but, well, it was a lie. The problems around that is, if you have data types, they need to be similar for one field across types, because Lucene doesn't know that concept. So, for example, if you have 2 different types and you have a field deleted in 2 different of those types, and you try to have deleted in one of those types as a Boolean and in the other one as a timestamp when you actually deleted the user, that's not possible, because it needs to have the same data type. Also, you have things like sparsity, which is generally not great, because Lucene will always leave some disk space, even if a field is missing. That has been improved in Lucene 7, which is in Elasticsearch 6. That has been improved a bit, but there is still some overhead. And also, scoring is across types. And a lot of people are not aware of that. So, for example, if you're using TF-IDF or BM25 for scoring, you have this thing where it counts how many times does one specific token appear over all your fields, or in one field, but overall your documents. And that is across types. Well, because Lucene doesn't know that concept. And people were very confused about that. And so we're getting rid of that. And this is kind of a very long-term approach. So in 5.6, you could opt into that behavior to have only allow a single type per index. In 6, we are enforcing that by default. You could disable that in the configuration and still allow the creation of multiple types per index, but we really don't recommend it, because the pain will only hit you in 7 even harder then. In 7, if you are using the _doc type, it will be optional in the API. So then you can basically get rid of the type in your APIs, and in 8, basically, there are no more types and everything has been removed. This takes a long time, like this will be multiple years, but we're trying to spread out the pain and not have any breaking change in one major version, but you can basically rotate out the multiple types per index over a longer period of time, just to take that pain away. Oh, we still have time, because I have missed one sequence number example, actually. Just something, quickly jumping back to the sequence numbers, to to confuse you a little more, sequence numbers are always per shard. So if I create 10 shards and 1 replica, and just to show you, this looks something like this. These are all the shards we have now. If I write data to that one, you have the sequence number 0, you have another 0, you have a 0, you then have 1, 2, 0 again, because this is being counted up on a per shard level. Whereas if you have one ID, it will always go to the same shard. If you do that, you can see it's nicely incrementing. Okay, that was just the sequence number example that I missed earlier. Okay, so types. This is what I have inserted in 5, because in 5 you could have multiple types. You can see I have the index types, and I have the type field, which is type 1, type 2, and type 3. If you were creating the index in 5, you can import that into 6, and it's still working. What you cannot do is create an index in 6, like the no types index, which I create now. Now I'm using the type _doc. The one, you can pick any one, but you can only have one. We recommend _doc because that will help you make the call optional in the API in the future. If I try to have another type now, this will fail and will actually tell me, okay, there is already one type in your mapping. Now you're trying to add a second one, and you need to decide. You can only have one by default. And now often the question is, how do I migrate my old data to this new format? And this is what this reindex here does. So reindex basically takes data from the index types and migrates it to the index no types. And then we're using a script to actually upgrade the data or migrate the multiple types away. So what we're doing here is I say the ID is the concatenation of the type field and the ID. Since all of my types were using a document with the ID 1 to have the ID still unique, you need to concatenate the type and the ID. That makes sense. Next up, we're saying I use a custom field type, so not underscore type, but only type, and I set the value to underscore type to that. So if you want to filter down to a specific type, you can just use a regular filter on that field now, but this is just a custom field. And then the field underscore type that is being removed, I replace that with underscore doc, which will become the optional one in the future. And if I run that, it will tell me, okay, it has reindexed 3 documents successfully. And if I search for them, you can see this has actually worked. So I have the index no types. This was the one document I have inserted there initially. And now here we have the other documents that I have migrated. So you can see the ID is the old type that I have, dash the ID. And then just the regular documents in a no types index with an underscore doc type. So that's all simple and easy. And now we're almost, I think we're already at the last example now. Some quick theory in between. It's just some clever algorithms that I really like. In 6.0, we have added something called automatic queue resizing. So what you do is you can basically say for one specific thing, I want to hit a specific latency, for example, or a specific response time. What I'm doing here is I'm saying for my searches, they should be a search should respond within 2 seconds. Otherwise, that node might be too busy, and I will rather fail that request and retry it than try on an overloaded node to wait for too long. So what you need to configure there is you need to say like, okay, my response rate is 2 seconds, and then depending on how many requests that index is serving or how many searches you're serving, that will determine how deep your queue is. So if you are currently doing 50 requests per second, if you can serve that, then the queue size will be 2 times 50, so the 2 seconds I have set at the response rate, times that how much you get through that, and that is how many elements you can have in the queue. If you have a 101st element you want to add to the queue, that one would be rejected rather than have it queued up too long. And that queue size calculation is done every 2,000 operations. By default, it will be recalculated how deep your queue should be to actually respond within the response rate that you have set. The other thing that we have added in 6.1 and which will be enabled by default in 7 only, right now you need to enable it manually, is adaptive replica selection. There is a nice paper to cut tail latency with adaptive replica selection. And what this does basically is, right now, if you do any read operation, we're basically round-robining it between all the nodes that have the data. So either the primary or the replicas, we will go to any one of them and just ask them for the result. What this paper does is basically it calculates this exponentially weighted moving average. So it basically finds out which nodes are the least busy, and it will then not round robin randomly between the nodes, but go to the least busy node. So if you have a node that is currently doing a garbage collection, is therefore very slow, rather than go to that node and wait or add more load to that node, you would instead go to one of the nodes that doesn't have that much load right now, and basically spread out the load more evenly. And we have added some mechanism into the regular request to always kind of tell back when you do a request how busy the node is, so we can actually do that for the next query and see where to go. We have ran some statistics, and you can see generally the throughput improves for everything. If you have no load and one replica, well, there is not much change. But especially if you have like more replicas and you have higher load, then your throughput and also your latency improves a lot. So this is just picking the right shards to query, like the least busy one, to improve especially the latency, but also the throughput in your system. And the final example are shrink and split. These were one of the main complaints I had from people in the field. So shrink basically is you have like too many of something and you try to combine them. And you try to combine them in the right way. And sometimes this works and sometimes it doesn't. And yeah, you should be afraid of that. But we're trying to do the right thing here. What we're doing combining is, how many shards do we allocate by default? 5 primary and 5 replicas. So if I create a new document here and I show what is going on, you can see 5 primary and 5 replica, and that is all fine. What you can then do is I want to combine those into fewer shards because I don't need the shards. People sometimes ask, why do you want fewer shards? Shards are good to scale out because more nodes can share the load. The problem is every single shard has some overhead, especially in terms of memory and file handles. And you need to spread out your queries further. If you, for example, have like the daily index pattern for logs, for today's index, you probably want to have many shards to spread the write load. But tomorrow, you're only reading data and you're not writing anything, and then you could combine something into fewer shards. This is pretty much what I'm doing here. So what I'm then telling the system is like, I want to combine them, and you need to put at least one copy of each shard on the same node so we can efficiently combine that into one shard afterwards. So I will tell my system to get one copy of each shard on that Elasticsearch 3 node. And if you look at the nodes here, every single shard is on at least, or one copy is on the Elasticsearch 3 node. So you can see these ones here, you have the shards 0, 1, 2, 3, 4. Every single shard has a copy on the Elasticsearch 3 node. And what we are then doing is I take this index shrink, I call the _shrink API, and put the entire data into the index which I call trunk. So this is the source index and this is the target index. And that new target index has one shard. This is what I configure here. And when I run that here, you can see immediately this is what we are doing. So what you're basically doing is we're not copying the data right away because that would be pretty costly. We're hard linking the data from the different directories. This is why this operation is pretty much instantaneously. So to combine the data, we're basically hard linking. That's also why you need one copy on each node. We're basically hard linking all those Lucene indices, shards, and then the segments together. And then you basically have just one primary and one replica shard here. You can also do the inverse operation now. The inverse operation is a violent process and looks pretty much like this when you try to split up data. What you need to do in 6.x, this will not be required in 7 anymore. You need to set a number of routing shards. And that number of routing shards basically defines into how many you can split something up. By the way, for shrinking down, is 5 a good number? Why not? Because it always needs to be a factor. And since 5 is a prime number, the only place where you can shrink down from 5 is 1. So if you pick a non-prime number, you have more options to shrink down. And the other way around, to split, we have a very similar concept. What split looks like is I create my split index, and here you say, I want to have one shard today, but I want to have like 20 synthetic shards. And I can split up into 20 of these synthetic shards in the future, or into 20 real shards. And this, again, can be done by any factor. So I pick 20 because 20 can be divided by lots of numbers. So you could split it up into 4 in the first step, or let's say into 5 in the first step, and then into 10, and then into 20 shards, or any factorization you can do of that number of routing shards. So let's create that index. Let's insert a document so I can prove in the end that it worked. If you look at it, you can see I have one primary and one replica shard. I need then to block write operations to this index. And then what I can do is I can say the split index, that is the source index, I call the underscore split API on that. And I want to put that into the split in 5 index afterwards. And that one has 5 shards. And 5 is a number or a factor of 20, which we have here. So if I do that, since it's hard linked again, this is very fast. You can see now I've broken up my index into those 10 different shards, 5 primary, 5 replica. And if you search for your data is still there. It all works as expected. Okay. Then people often ask me, okay, which one is the fastest system? I think in one of the previous talks there was this question like, what is faster, a relational database or a non-relational database? And I always show this comic for this because I think I couldn't find a good source for that. It's not from me, but I think this is really one of the best descriptions for this benchmarking problem. And this is every time some vendor puts out a benchmark and says like, our system is twice as fast as all these other systems, this is what you're getting. Because it really depends, A, what are you doing and under what conditions. And yeah, here under these conditions, well, the squid might be more intelligent because you drowned the house cat, but that doesn't make it much more intelligent in general. But this is what you get in every benchmark. We do benchmark a lot internally. We don't benchmark with competitors because that's not very the right thing to do. But we benchmark a lot internally to avoid this slow boiling frog problem. Anybody heard of the slow boiling frog? If you put the frog into the cold water and then turn up the heat slowly, it will think everything is normal and it will not jump out. Whereas if you throw the frog into the boiling water, it will try to jump out immediately. And you have kind of the same problem with benchmarks. If like you're doing one change and the performance degrades by 0.5%, nobody notices, and tomorrow's commit changes everything by 1%, and the day after you make something worse by 0.2% again. But over time, it's basically like boiling the frog and killing the frog. And that's what happens to your benchmarks, or in your benchmarks often, if you don't run them regularly. So we have written our own benchmarking tool now, and you can also use that for your own scenarios. So if you have some specific hardware setup or some specific scenario you're trying to test, you can also use this benchmarking tool to actually benchmark what is the performance you can get out of that system. But it is not kind of like the right thing to compare different systems. You can only do that internally in general. Okay, to wrap up, we've seen a lot of stuff. It's kind of like the growing up of Elasticsearch, like being more strict, and trying to make upgrades easier, hitting some limits and then trying to correct them, some clever performance improvements, and at the end, shrink and split, something that people often wanted because before you basically had to re-index all your data to change the number of shards. Now it's a bit easier and you can actually fix that problem. And with that, we're done. I always take a picture so I can prove to my colleagues that I've been working today. Because nobody really knows where I am. We are fully distributed, and I don't go to an office. Let's see. Maybe we don't have that much light here. Smile, everybody. Very good. Are there any questions in the room? No? Okay. I think we're pretty much out of time. Let me quickly check Slido. That's not what I wanted. Did anybody enter any questions? What is the best way to create automated tests for elk stack configuration? I'm not sure about what exactly do you want to test? That it starts up correctly or that the performance is right? Because starting up, I can kind of imagine, yeah, you configure it, and if it starts up, you have kind of configured it correctly. Or if you want to do performance regressions, then you would probably need Rally. So if you just want to know, like, since we will fail the node if we don't recognize a parameter, you can check the correctness quite easily. For performance regressions, you would probably need to run something like Rally. That's pretty much it. Yeah, if you have other questions, come to me afterwards. There are some stickers over there, so if you want to have some more stickers, as long as there are some left, grab them. And thanks for now.